Hello and welcome to this presentation on complex numbers, where we're going to review DeMoivre's theorem for looking at roots and higher powers of complex numbers. We will also look at the exponential form of complex numbers and converting between various forms of complex numbers. This presentation assumes you have seen two previous presentations, one on the Cartesian form of complex numbers and one on the polar form of complex numbers. We'll be using the knowledge in those presentations to underpin the work in this presentation. Presentation overview. We're going to introduce DeMoivre's theorem. We're going to use it to find square roots of complex numbers, to find higher roots of complex numbers, the third and the fourth roots. We're also going to look at the exponential form of complex numbers and how to convert between different forms of complex number. DeMoivre's theorem. Let's review powers of complex numbers. Let's assume we have two complex numbers in polar form, r argument theta multiplied by r argument theta. In polar form, to multiply, we multiply the moduli and add the arguments. So in this case, r times r is r squared, and adding the theta to the theta, we get 2 theta. So the r theta times r theta is r squared argument 2 theta. Similarly, if we have r angle theta multiplied by r angle theta multiplied by r angle theta, in polar form that will be r times r, which is r cubed, and then add these 3 thetas together, we get argument 3 theta. The above results are generally expressed in what is termed DeMoivre's theorem, which states that r argument theta, all raised to the power of n, can be written in polar form as r to the power n, n times theta for the argument. This result is true for all positive, negative and fractional values of n. DeMoivre's theorem is used to find powers and roots of complex numbers. Square roots of complex numbers. A square root of a complex number can be determined as follows. The square root of r argument theta, polar form, can be written as r argument theta raised to the power of a half using our fractional index notation. Applying DeMoivre's theorem, that can now be written as r to the power of a half, argument a half times theta. Remember, a real root has two square roots, equal in magnitude but opposite in direction. For example, if we want to find the square root of positive 9, the two solutions are positive 3 and negative 3, because positive 3 multiplied by positive 3 equals positive 9, and negative 3 multiplied by negative 3 is positive 9. So there are two solutions equal in size but opposite in sense. The figure on the right shows an Argand diagram that relates to two square roots of the complex number 169 argument 45.2 degrees. There are two solutions for the square root of this complex number represented by the blue and purple phasors shown. Note that the phasors are 180 degrees apart, so this angle in here is 180 degrees. So to find our two roots, they're 180 degrees apart, we go through the following process. 169 argument 45.2 degrees, all square rooted to the power of a half, can be written using DeMoivre's theorem as 169 to the power of a half, argument a half multiplied by 45.2 degrees. So 169 square rooted is plus or minus 13, and a half multiplied by 45.2 degrees is argument 22.6 degrees. So there are two solutions stated in polar form. The first root is 13 magnitude, an angle of 22.6 degrees on the horizontal, and the second solution for the square root is a magnitude of 13 but an angle of negative 157.4 degrees on the horizontal. Note 157.4 degrees plus 22.6 degrees is 180 degrees. If we now want to convert the roots in polar form to Cartesian form, we undertake the following process. So given positive and negative 13 angle 22.6 degrees. Using the conversion from a previous presentation, we write that as positive and negative 13 in brackets cos of 22.6 degrees plus j sine of 22.6 degrees. If you evaluate that expression, you will get positive and negative 12 plus j phi. In other words, positive and negative 13 multiplied by the cos of 22.6 degrees will give you positive and negative 12. And the positive and negative 13 multiplied by j sine 22.6 degrees will give you plus or minus j phi. I'll let you undertake the calculations for yourself. So on the Argand diagram in Cartesian form, the first root is 12 plus j5, so 12 plus j5 shows us this phasor here. And the second root is negative 12 minus j5, so negative 12 on the real axis, negative 5 on the j-axis shows us the second root here. So the two square roots related to the 169 argument 45.2 degree complex number are shown on the diagram, and they are both 180 degrees apart from each other. Example 10. We're asked to evaluate in polar form the following complex numbers given in Cartesian form. So part 1. 4 plus j2 all raised to the power 3. So part 1, initially given the Cartesian form of 4 plus j2 all to the power 3, we're going to convert that into the polar form of our argument theta to the power n. So to work out r, the modulus or the magnitude of our complex number, r is equal to, from Pythagoras' theorem, 4 squared plus 2 squared all square rooted, so that's equal to 4.472. And to work out the angle theta in our diagram, don't forget it's always measured positive from the real axis in an anti-clockwise direction. That will be theta equals to tan to the minus 1, the arctan of the opposite side 2 divided by adjacent side 4, and that's equal to 26.565 degrees from our calculator. So now we can write our complex number of 4 plus j2 in polar form. That will be 4.472 argument 26.565 degrees all to the power of 3. Applying DeMoivre's theorem, that now becomes 4.472 to the power of 3, argument 3 times the 26.565 degrees. Evaluating that gives us 89.43 for the modulus, and the argument is 79.7 degrees. Part 2, we're given the Cartesian form of a complex number 3 plus j4, and this is raised to the power of a half, so we're looking for a square root here. So in part 2, we've got a 3 plus j4 to the power of half. We're going to convert that into polar form, the r argument theta format. So the r in this case will be 3 squared plus 4 squared all square rooted. This gives us 5 from Pythagoras' theorem. And theta is equal to the arctan, or tan to the minus 1, of the opposite side 4 on the imaginary axis divided by the adjacent side 3 on the real axis. That gives us 53.13 degrees. So in polar form, 3 plus j4 can be written as 5 argument 53.13 degrees, and this is now raised to the power of a half. So again, applying DeMoivre's theorem, that becomes 5 to the power of a half, argument a half multiplied by the 53.13 degrees. Evaluating that, we get 2.236 for the square root of 5 in 3 decimal places, argument 26.57 degrees. The second root being 180 degrees apart, we get 2.236, argument 206.57 degrees. That's 180 degrees added to the 26.57 degrees. There's our 2 solution. Questions 39 to 42 require us to find the powers of the complex numbers given, stating these solutions in both Cartesian and polar form. Question 39 part A, we're asked to find 2 plus j3 all squared. That could be done by using binomial bracket expansion in Cartesian form and simplifying the resultant expressions, noting that j squared is equal to a negative 1. Or you could convert it into polar form, solve it in polar form using DeMoivre's theorem and then revert it back into Cartesian form. Same applies to part B. Same process could be adopted there. Solutions are given in the square brackets here. In question 40, we're asked to find negative 3 plus j2 all to the power of 5. Now, because that's to the power of 5, I don't think I would want to go through that in a Cartesian form. I think I'll put that straight into polar form, use DeMoivre's theorem to find the solution, and then convert into Cartesian form. And the same for part B with the negative 2 minus j cubed term. Again, solutions are shown in the square brackets. Question 41 part A has a complex number in polar form that's raised to the power of 4. So using DeMoivre's theorem immediately we could work out the solution in polar form and convert to Cartesian form, and the same approach applies to part B. Again, the answers are in the square brackets. Question 42 part A, we've got 3 argument negative pi upon 3, that's obviously angle in radians, cubed, so again using DeMoivre's theorem, solve that in polar form and then convert to Cartesian. And the same approach to part B with the complex number in polar form raised to the power of 4. Solutions again in the square brackets. Questions 43 to 45. This time we're asked to evaluate the square roots of the complex numbers given and then plot the roots on an Argand diagram. So question 43 part A, complex number is in Cartesian form, 2 plus j. We need to convert that to polar form and use DeMoivre's theorem to find the roots, and the same approach with part B. Solutions are in the square brackets. Question 44, a very similar approach to that of question 43, and again the solution in the square brackets. Question 45, part A, we're given a complex number in polar form, so we can immediately use DeMoivre's theorem here to find the roots in polar form and then convert them into Cartesian form. And then part B, again we're given another complex number in polar form, this time the angle's in radians, but again the same approach, we can use DeMoivre's theorem, find the roots in polar form and then convert to Cartesian form. Answers are in square brackets. Question 46, we're given a complex number z is equal to 3 argument 30 degrees in polar form. We've got to evaluate part A, z squared, and part B, the square root of z. So again we can use the DeMoivre's theorem here to solve that problem. Answer in the square brackets. Question 47, we're asked to convert the complex number in Cartesian form of 2 minus j, put that into polar form, and so evaluate 2 minus j all to the power of 7. Solutions are shown in the square brackets. Question 48, we're asked to simplify the following. The cos of pi upon 9 minus a j sine pi upon 9, all raised to the power of 4, and that's all divided by cos pi upon 9 plus j sine pi upon 9 to the power of 5. What I suggest we do here is evaluate the numerator and denominator in terms of Cartesian form, then convert them into polar form, apply DeMoivre's theorem to raise the numerator to the power of 4, denominator to the power of 5, and then look for simplification using polar form division. Solution should be negative 1. Finding higher roots of complex numbers. In general, when finding the nth root of a complex number, there will be n solutions. So for example, in Cartesian form a plus jb raised to the power of a third, there will be 3 roots to find. X plus jy to the power of a quarter, there will be 4 roots to find. Each root will have the same modulus, the same magnitude, but spaced 360 degrees divided by n apart, where n is the number of roots. So to find roots of complex numbers, we use the following approach. Step 1, we apply DeMoivre's theorem to first find the n root, the first root. Step 2, we find all other roots by equally distributing them around the Argand diagram at intervals of 360 degrees upon n. We'll apply this principle in the following examples. Finding higher roots of complex numbers continued. So a complex number has two square roots separated by 360 degrees upon 2, that's 180 degrees apart, or in radians, that's pi radians. Three cube roots are separated by 360 degrees upon 3, that's 120 degrees, or 2 pi upon 3 radians. And four roots are separated by 360 degrees upon 4, so that's 90 degrees apart, or pi upon 2 radians. And so it goes on. Example 11. We're asked to determine the roots of 3 plus j5 to the power of a third. So we're looking for three roots here. The first step is to convert from Cartesian to polar form. So noting that r cos theta plus jr sin theta is equal to r argument theta. 3 plus j5 into polar form, the modulus r is equal to, this is Pythagoras theorem, 3 squared plus 5 squared all square rooted, so the modulus r is 5.831. Note that the complex number resides in the first quadrant because it's positive 3 on the real axis and positive 5 on the j-axis, the imaginary axis. So the argument angle theta is simply given by the tan to the minus 1 of the 5 divided by 3 in this case, which is 59 degrees. So we can write the Cartesian complex number 3 plus j5 as 5.831 argument 59 degrees in polar form. We're raising that to the power of 1/3. Applying DeMoivre's theorem, then that becomes 5.831 to the power of a third, argument 59 degrees divided by 3. Evaluating that sum, 5.831 to the power of a third, in other words the cube root of 5.831 is 1.8, and 59 degrees divided by 3 is 19.7 degrees. So our first root is 1.8 argument 19.7 degrees. The other roots are obtained by noting that they are spaced 360 degrees divided by 3, which equals 120 degrees apart. These are cube roots and are spaced equally 110 degrees apart. Example 11 continued. So from the first slide we found the first of our cube roots was r, 1.8 at an angle of 19.7 degrees. So now looking for the other roots, the second root will be 1.8 argument 19.7 degrees plus 120 degrees. So the second root is 1.8 argument 139.7 degrees, so that will be this phasor shown here. And the third root will be 1.8 argument 139.7 degrees plus 120 degrees, so 1.8 argument 259.7 degrees, which will be this phasor here. So those are our three roots required when we're taking the cube root of 5.831 argument 59 degrees. Now we convert into Cartesian form using the equation shown on the previous slide. So 1.8 argument 19.7 degrees in Cartesian form will be 1.8 cos of 19.7 degrees plus j 1.8 sine of 19.7 degrees. So therefore the 1.8 argument 19.7 degrees is equal to 1.695 plus j 0.6068 in Cartesian form. And similarly calculating the other roots that are given above, the second root is negative 1.373 plus j 1.164, and the final root is negative 0.3218 minus j 1.771. So those are our three roots in both polar form and Cartesian form. Exercise 7, we're asked to determine the moduli and arguments of the following complex roots. I would encourage you to stop the presentation here and attempt parts A, B, C and D. The answers are shown in the square brackets on the right hand side. Full solutions are shown on the following slides. Exercise 7 solutions. Part A. We're given the complex number 6 plus j2 all raised to the power of a third, so we're finding the cube root of that Cartesian complex number. First thing we'll do is plot it on an Argand diagram. So 6 on the real axis, 2 on the imaginary j-axis gives a phasor here that represents the complex number. We're now going to convert this from Cartesian form into polar form, r argument theta format. So modulus r from Pythagoras' theorem, r is equal to square root of 6 squared plus 2 squared in this case. That gives us a value of 6.325. And the argument, angle theta, is the tan to the minus 1 of 2 divided by 6. So that gives us a value of 18.435. So we now have our r value and our theta value in polar form. Notice from the Argand diagram our phasor is in the first quadrant, so therefore we can work out the argument theta directly from our arctan formula. So now in polar form the complex number is 6.325, argument 18.435, and we're raising that to a power of a third. So using DeMoivre's theorem, that gives us 6.325 to the power of a third, and the argument is 18.435 divided by 3. So the cube root of 6.325 is 1.849, and 18.435 degrees divided by 3 is argument 6.145 degrees. The other roots are found by spacing each of the phasors 360 degrees divided by 3, in other words 120 degrees apart in this case. So our first root is drawn here, r is equal to 1.849 and angle theta is 6.145 measured anti-clockwise from the real axis. The second root is simply found by adding 120 degrees to the first root, so the second root is 1.849 argument 126.145 degrees, so that will be this phasor here with the r the same as the first phasor, and don't forget the angle is measured from here round, so that angle there is the 126.145 degrees. And to find the third root, the final root, we add 120 degrees to the 126.145 degree angle, and that gives us the root at 1.849 argument 246.145 degrees. And again, if we add that on our Argand diagram, we will find we're measuring from the horizontal axis right the way around to here. This is the 246.145 degree. So those are the three roots stated in polar form related to the complex number 6 plus j2 given in part A of the exercise. Exercise 7 solutions continued. This is part B. We're given the complex number -2 plus j all to the power of a quarter. We plot this on an Argand diagram, then -2 on the real axis, +1j on the imaginary j-axis. Our phasor resides in the second quadrant of the Argand diagram. So angle theta we must measure. Don't forget it's always measured from the real axis in anti-clockwise direction, positive. So the first thing we're going to do is convert the Cartesian complex number given, the -2 plus j, into the polar form of r argument theta. So from Pythagoras' theorem, the modulus r is the square root of 2 squared plus the 1 squared in this case, which is 2.236. And I'm going to calculate first of all angle alpha. And angle alpha is the angle in here in this particular case, and it's measured here as shown. So angle alpha is the tan to the minus 1 of the opposite side 1 divided by the adjacent side -2, and that's a value of -26.565 degrees. So don't forget, we always have to specify our angles positive from the real axis in an anti-clockwise direction to get the actual value of theta. So in this case, the argument theta is 180 degrees. Take away the 26.565 degrees calculated above. So angle theta is 153.435 degrees. Just be careful there how we worked out our angle theta. We now have the complex number in polar form, so 2.236, argument 153.435 degrees is raised to the power of a quarter. We're trying to calculate 4 roots here. So applying DeMoivre's theorem, we get 2.236 to the power of a quarter, argument 153.435 divided by 4 in this case. That resolves to the fourth root of 2.236 is 1.223, and 153.435 divided by 4 is 38.36 degrees. So that's our first root that we've calculated, and all other roots are obtained by noting they are spaced 360 degrees divided by 4, the fourth root in this case, that are spaced 90 degrees apart on the Argand diagram. Exercise 7, part B continued. We're trying to find the fourth root of the negative 2 plus j complex number. From the previous slide we found the root of r is equal to 1.223, argument 38.4 degrees. So that's the first root we're looking for. To find the other roots, we simply equally space each of the roots by 90 degrees. So we add 90 degrees to the first root here, so the second root is 1.223 argument 128.36 degrees. That will be the phasor shown here, the same value of r, but of course the argument is measured from the horizontal real axis around to here, and that's the 128.36 degrees. To find the third root, we simply add 90 degrees to the second root, so that's 1.223 argument 218.36 degrees, so that will be the phasor shown here. And to find the fourth and final root, we add 90 degrees to the third root, so the final root is 1.223 argument 308.36 degrees, and that's the root shown here. We want to convert them into Cartesian form, then we know r argument theta can be written in terms of r cos theta plus jr sin theta from previous work. So we take the first root, that's 1.223 argument 38.360 degrees, then in Cartesian form that will be 1.223 cos of the 38.360 degrees plus the j 1.223 times the sine of the 38.360 degrees. Evaluating that expression, then the polar form 1.223 argument 38.360 degrees can be written as 0.9590, the real part plus the imaginary part, and the j 0.7590. And we can adopt the similar approach for all the other roots that are shown below. So the second root in terms of Cartesian form is shown here, the third root in Cartesian form shown here, and the final and fourth root in Cartesian form shown here. Exercise 7, solutions continued. This is part C. We're asked to find the square root of negative 6 minus j5. If we plot this Cartesian complex number on an Argand diagram, we get negative 6 on the real axis, negative 5 on the imaginary j-axis. So our phasor resides in the third quadrant. Don't forget we always measure angle thetas from the real axis in an anti-clockwise direction to the phasor. So we're going to now convert the Cartesian complex number negative 6 minus j5 into polar form, the r theta format. Calculate the modulus r, that's from Pythagoras' theorem 6 squared plus 5 squared in this case, all square rooted, the value of 7.81 for r. Now to calculate angle theta, the first thing I'm going to do is calculate angle alpha, which is this angle shown here on our diagram. And once I know angle alpha, I can work out angle theta. So in this case, angle alpha is found by using the tan to the minus 1 of the opposite side of our triangle. It's negative 5 in this case divided by the adjacent side, negative 6. So that gives an angle of 39.8 degrees. Now we always measure angle theta in an anti-clockwise direction from the real axis. So angle theta will be this angle shown on our diagram. So to work out the argument theta in this case is 180 degrees plus the 39.8 degrees, so 219.8 degrees. So in polar form, we now can write the complex number as 7.81 argument 219.8 degrees, and we're trying to find the square root, power of a half. So applying DeMoivre's theorem, we write that as 7.81 to the power of a half argument 290.8 degrees divided by 2. So 7.81 square rooted is 2.795, and the argument is 219.8 divided by 2, so that's 109.9 degrees. We can calculate all the other roots simply by noting they are equally spaced by the angle of 360 degrees divided by 2 in this case, because we're looking at square roots, so they're 180 degrees apart on the Argand diagram. Exercise 7 solutions continue for part C here. So from the previous page, we know that the first root we found is in the second quadrant, the R is 2.795 and the argument is 109.9 degrees, so that's the position shown there. So if we want to find the second root, in this particular case, we simply add 180 degrees to the original angle. So the second complex number root is 2.795 argument, and 109.9 degrees plus 180 degrees is 289.9 degrees. So on the Argand diagram, this would be the second square root in this particular case. The R is the same as the first, but the angle is 180 degrees further around on the diagram. If we now want to convert into Cartesian form from the polar form, the R argument theta form, we use the R cos theta plus GR sin theta formula. So taking the first square root, the 2.795 argument, 109.9 degrees, then that's going to be written as 2.795 cos of 109.9 degrees plus the J 2.795 sine of 109.9 degrees. Evaluating that, we get a Cartesian complex number of negative 0.9514 plus the J 2.628, and we can adopt a similar approach to find the other root. That will give us a Cartesian complex number with a change of sign in this case. Exercise 7 solutions continue. This is now part D. We're given the complex number 4 plus J3 raised to the power of negative 2 divided by 3. Plot the complex number on the Argand diagram, 4 on the real axis, 3 on the imaginary axis, so we're in the first quadrant of the Argand diagram. If we convert from Cartesian form, 4 plus J3, into the polar form R argument theta, the modulus R is the square root of, in this case, 4 squared plus 3 squared, so that's 5. And angle theta can be calculated directly because we're in the first quadrant, so tan to the minus 1 of 3 divided by 4 is 36.87 degrees. So we've worked out our R and our theta now. So now in polar form, our complex number is 5, argument 36.87 degrees, and that's raised to the power of negative 2 divided by 3. So using DeMoivre's theorem, 5 to the power of negative 2 divided by 3, argument negative 2 multiplied by the 36.87 degrees divided by 3. Evaluating, we get 0.342, argument negative 24.58 degrees. Don't forget the other roots are obtained by equally spacing them. In this case, it will be 360 divided by 3, because that's the root we're looking at, and that's 120 degrees apart. So notice we just used the 3 in this case, because that relates to the root part of the negative 2 upon 3 power. So to find the other roots, we simply add 120 degrees to the previous root. So the second root will be 0.342 argument. Now negative 24.58 plus 120 degrees is 95.42 degrees. And then for the third root, we add 120 degrees to the second root. So that's going to be 0.342 argument 215.42 degrees. I'll let you check those figures. Exercise 7D continued. We're solving 4 plus J3 in a bracket, all raised to the power of negative 2 divided by 3. So from the previous slide, our first solution was shown here for the phasor of R is equal to 0.342 magnitude in angle of negative 24.58. That's the angle shown here in this direction clockwise from the real axis. Our second solution is shown here on the Argand diagram. R is equal to 0.342 again, and this time the angle is positive 95.42 measured anti-clockwise from the real axis as shown. In other words, solution 1 and solution 2 are 120 degrees apart. And the third solution we're given is shown here in the third quadrant of the Argand diagram. R is equal to 0.342, and that's at an angle of 215.42 degrees positive. So the 215.42 degrees is shown here on the Argand diagram. All solutions are equally spaced at 120 degrees. If we now want to convert into Cartesian form, we currently have the R argument theta format, the polar format, and to convert that into Cartesian form we use the R cos theta plus GR sin theta expression. So considering the first solution, a 0.342 argument, negative 24.58, converting that into a Cartesian form, we get 0.342 cos of negative 24.58 plus the j 0.342 sine of negative 22.58. Evaluating that expression, we get 0.311 minus j 0.1423. We can adopt the same approach for calculating the other solutions in Cartesian form. I'll let you go through the calculation process yourself, but you should find them for the second solution. We get negative 0.0323 plus j 0.3405. And the third solution is negative 0.2787 minus j 0.1982. I'd encourage you to check those calculations for yourself. We're now going to consider the exponential form of a complex number. Now, certain mathematical functions can be expressed as what are termed power series, and three such series are shown below for reference. The e to the x series, 1 plus x to the 2 upon factorial 2 plus x to the 3 upon factorial 3, etc. Call that equation 1. We have the sine x power series written as x minus x cubed upon factorial 3, etc. Call that equation 2. And we have the cos power series written as 1 minus x squared upon factorial 2 plus x to the 4 upon factorial 4, etc. Call that equation 3. There are proofs behind those, but they're given without proof for our reference. Exponential form of a complex number continued. Now, if we replace x in equation 1 on the previous slide with the imaginary sum j theta, so this was the equation on the previous slide for reference, but we're going to replace all the x terms in the expression with now j thetas, and then raise these j thetas to the appropriate powers given. What we will end up with are terms like j squared in j cubed, j to the 4, j to the 5, j to the 6, etc. Now, from a previous presentation we had on the powers of j, we noticed that j squared can be written as negative 1. J cubed can be written as negative j. J to the 4 is actually unity, or 1. And then the pattern repeats itself. So j to the 5 is actually j, j to the 6 is negative 1, and so the pattern goes on. So what we now have is an e to the j theta power series instead of an e to the x series we had in equation 1, which can be written as 1 plus j theta minus theta squared upon factorial 2 minus j theta cubed upon factorial 3 plus theta 4 upon factorial 4 plus j theta 5 upon factorial 5, and so it goes on. And in that expression we've accounted for the positive and negatives of the previous line. Exponential form of a complex number continued. Now, if we were to group the real and imaginary terms from the previous slide for e to the j theta power series, we'd note the following. For the real terms, we would have 1 minus theta squared upon factorial 2 plus theta to the 4 upon factorial 4, etc. If we now consider the imaginary terms of the e to the j theta series on the previous slide and group them, we'd get plus j, and in the bracket theta minus theta cubed upon factorial 3 plus theta to the 5 upon factorial 5, etc. Just considering the real terms now, we notice they're very similar in their power series format to that of cos x, or equation 3, on the previous slide. I've repeated it here for convenience. The power series cos x was equal to 1 minus x squared upon factorial 2 plus x to the 4 upon factorial 4, etc. And that's the format we've got in our j theta series. So we could write on the right hand side of the e to j theta power series cos theta for all the real terms. If we now consider the imaginary terms in the above e to j theta power series, they look rather similar to the sine theta or sine x series as shown in equation 2 and repeated here for convenience. The sine x series has x minus x to 3 upon factorial 3 plus x to 5 upon factorial 5, etc. And that's the format we see in the e to the j theta series. So we could write on the right hand side of the e to the j theta power series plus j sine of theta. And I've called that equation 4 here. So now if we replace theta in equation 4 with a negative theta, we could write the e to the j theta power series now as e to the negative j theta power series. But we've got to then change the sign of these thetas on the right hand side. So we get cos of negative theta plus j sine of negative theta. If we now consider the curves on the right hand side, here is the cosine curve plotted for us. What we notice is that for a value of, say, positive 60 degrees as an angle, if we draw that up till it hits the curve and then read across for the ratio, we get a positive 0.5 value. But if we had a negative value of the angle, so negative 60 degrees, and we draw that vertically up and then along so it hits the vertical axis, we again get the 0.5 value for ratio. So whether our angle is positive or negative, we get the same value on the cosine curve. And that's because it's what's called an even curve. If we now consider the sine curve, which is this curve here on the diagram, and we consider values of 90 degrees, for example, then at positive 90 degrees on the right hand side, if I draw a line vertically up till it hits the sine curve, and then a line horizontally across till it hits the vertical axis, I find I get a ratio of positive 1. If I consider the negative 90 degrees on the left hand side of the vertical axis, and draw a line down until it hits the curve, and a line across till it hits the vertical axis, I find I get a negative ratio, negative 1 in this case, an opposite sense. So what we're saying here, when we have a cos of a negative angle, that's the same as a cos of a positive angle. But if we have a sine of a negative angle, that's actually the change in sign of the sine of the positive angle. So in other words, sine of minus 90 degrees is negative 1, but sine of 90 degrees is positive 1. So by putting the negative in front of the sine function, we can equate left and right hand sides there. So if I change the sign on the right hand side in equation 5 here of the sine function, then I can write the e to the minus j theta equation. I would encourage you to stop the presentation and just rethink through the information on that slide. Exponential form of a complex number continued. So the polar form of a complex number, r argument theta, can be written as r and in brackets cos theta plus j sine theta from our previous work. So that's going from the polar form on the left hand side to the Cartesian form on the right hand side. But we note from equation 4 on the previous slide that cos theta plus j sine theta is equal to e to the j theta. So in other words, this Cartesian form on the left hand side is equal to e to the j theta. So we could now write a complex number z as equal to r, and instead of multiplied by cos theta plus j sine theta, it's multiplied by e to the j theta. And this form is called the exponential form of a complex number. So this is another form of expressing complex numbers. So here's a summary of the 3 ways of expressing complex numbers. Firstly, in Cartesian form, sometimes called rectangular form, z is equal to a plus jb. For example, that could be x plus jy is equal to 4 plus j3, where x is 4 and y is 3. Secondly, in polar form, where z is equal to r argument theta. So for example, r argument theta could equal to 5 argument 36.5 degrees, or r argument theta could equal to 5 argument 0.63, and that would be radians. And thirdly, in exponential form, the z is equal to r e to the j theta. It's a type of polar form. In polar form, we can have r in angle theta, or r in angle radians, but in exponential format we are only allowed to have the angle theta in radians. So for example, r e to the j theta is equal to 5 e to the j 0.63. That 0.63 is in radians. It cannot be in degrees. So important note, always remember you must use radians when you're using the exponential form of a complex number. That is very important to remember. Example 12. We're asked to change the Cartesian complex number 3 plus j4 into polar form and then into exponential form. So plot on the Argand diagram, 3 on the real axis, 4 on the imaginary axis. We're obviously in the first quadrant here. So to convert 3 plus j4 into polar form, our argument theta format, r, don't forget, is the modulus, theta is the argument. So from Pythagoras theorem, r is equal to the square root of 3 squared plus 4 squared, so that's 5 in this case. And angle theta can be directly calculated from the tan to the minus 1 equation we use. So tan to the minus 1 of the opposite side 4 divided by adjacent side 3 is 53.13 degrees, or in radians 0.927 radians. So in polar form we have 5 argument 0.927 radians, and in exponential form we can write that as 5 e to the j 0.927. So that's the e to the j theta form. Example 13, we're asked to convert in part A 6.4 multiplied by e to the j 1.5 into Cartesian form. So let's look at that one first of all. For part A, 6.4 e to the j 1.5, that's in the form r is equal to e to the j theta. Let's first of all convert to polar form, the r argument theta format. So r in this case is 6.4, theta is 1.5 radians, or if you want to convert it to degrees, is 86.94 degrees. So in polar form, r argument theta is equal to 6.4 argument 86.94 degrees. To convert that into Cartesian form, we use the following equation: x plus jy is equal to r cos theta plus jr sin theta from a previous presentation. So in this case, x plus jy is equal to the r 6.4 multiplied by the cos of 86.94 degrees plus j 6.4 multiplied by the sine of 86.94 degrees. Evaluating, x plus jy is equal to 0.3416 plus j 6.3908. So the x is 0.3416 and the y is 6.3908. Part B of example 13 wants us to convert 2.1 e to the power of 3 plus j 0.25 into Cartesian form. So part B, 2.1 multiplied by e and then to the power of, I put it in a bracket for convenience here, 3 plus j 0.25. Using the first law of indices, I'm going to slightly simplify that, we get 2.1 e to the power of 3 multiplied by e to the power of j 0.25. Now we can evaluate 2.1 multiplied by e to the power of 3, because e to the power of 3 is 20.086, 3 decimal places, and that's multiplied by e to the j 0.25. So on evaluation we get 42.1806 multiplied by e to the power of j 0.25. And we can equate that to the format r is equal to e to the j theta, reading that r in this case is 42.1806 and angle theta is 0.25. Now to convert to Cartesian form, as in part A, we just use the x plus jy is equal to r cos theta plus jr sin theta. I'll let you put the values in here. You should end up with x plus jy is equal to 40.869 plus j 10.435. I'll let you review that solution at your own pace. Exercise 8 consists of 7 parts. In part 1 we've got to express the complex number z equals to 4e to the power of 1 plus j pi upon 3 into Cartesian form. Similar approach required in part 2. In part 3 we're asked to change the Cartesian form of a complex number into exponential form. Similar in part 4. In part 5 we're given an exponential form, we've got to put it into Cartesian form. Part 6 we've got an exponential form, again has to go into Cartesian form. And part 7 we've got an exponential form, again into Cartesian form. Answers are given in the brackets on the right hand side. I would encourage you to stop the presentation, work through these 7 little questions before comparing your answers with the solutions on the following slides. Here are the solutions to exercise 8. I'm going to let you wander through them at your own pace, but part 1 here we're given a complex number in terms of exponential form and we've got to convert it to Cartesian form. So notice I started off by using the first law of indices to slightly simplify the equation from where I can go into polar form and then into Cartesian form. Solutions given at the bottom for Z. Exercise 8 part 2 solution. Again we're changing from the exponential form into Cartesian form here, making use of the first law of indices along the way. Exercise 8 part 3. I've just sketched the complex number given the Cartesian 5 plus j3 on the Argand diagram, so I know clearly where my phasor resides before I start converting to polar form. Finally got to end up with exponential form in this case. Exercise 8 part 4. I'm given a Cartesian complex number to put into exponential form, so don't forget the first thing to do is make sure you plot it. Negative 2.5 on the real axis, 4.2 on the imaginary j-axis, so the phasor resides in the second quadrant. But don't forget angle theta must be calculated from the real axis in an anti-clockwise direction. I initially started this problem by trying to find angle alpha, and that is this angle shown here on my diagram, and the calculations are shown below. Once I know angle alpha, I can simply take that from 180 degrees to get angle theta in this case. Then I can write it in polar form and into exponential form. Exercise 8 part 5, we're given an exponential form of a complex number and we've got to convert that into Cartesian form. Solution given here at the bottom. Exercise 8 continued, part 6 solution. We're given a complex number in terms of exponential form and we've got to convert it into Cartesian form. Again we make use of the first law of indices here to help simplify the problem. Answer shown in Cartesian form here. And exercise 8 part 7, we're asked to convert an exponential form of a complex number into rectangular form, which is Cartesian form. Again we will make use of the first law of indices. Just watch out for your negative value for the argument. Example 14. We're given the complex number z is equal to 5e to the power of j 1.3. We've got to determine ln z in this case in both the Cartesian and the polar form. So given that z is equal to 5e to the j 1.3, we're going to take natural logarithms of both sides of the equation, that's the ln function. So on the left hand side we get ln of z, on the right hand side we got ln of the 5e to the j 1.3. So using logs to help us solve this problem, we're going to apply the first law of logarithms to the right hand side of the equation. Now the first law of logarithms says that when you've got log of, in brackets, a multiplied by b, that's the same as log of a added to the log of b. Now on the right hand side of our equation we have ln of 5e to the j 1.3. Now it's an ln function, but don't forget the laws of logs apply to any base. We've got the base of e here. And inside the bracket the 5 is effectively the a term and the e to the j 1.3 is the b term. So applying the first law of logarithms to the right hand side, we can write that as ln 5, which is a number, it's a button push on a calculator, plus the ln of e to the j 1.3. So we end up with the Cartesian form on left hand side ln z is equal to 1.6094, that's ln 5 typed on your calculator, plus j 1.3. And we get the j 1.3 because the ln and e functions cancel each other out. Don't forget ln and e are inverse functions. So we end up simply with the j 1.3. This obviously lies in the first quadrant because we've got a positive real value and a positive imaginary value. So on an argand diagram, we're in the first quadrant. So now calculating into polar form, that's the R argument theta format, we get ln z is equal to the modulus of the above Cartesian form will be 1.6094 squared plus 1.3 squared all square rooted, that's Pythagoras theorem to find the modulus, and the argument, the angle in this case 10 to the minus 1 of the 1.3, the opposite side divided by the adjacent side, 1.6094 on our argand diagram. So ln z can be written as 2.0689 argument 39.9 degrees, or 2.0689 argument 0.696 radians. I encourage you to stop the presentation here and review the steps in that calculation. Exercise 9, part A, we're given complex number z in exponential format, 4e to the 1 minus j. If it helps you, you can think of brackets around the exponent here. We've got to determine ln z in polar form. In part B, we've got to evaluate in polar form ln of the complex number 3 plus j4. Part C, we're given z is equal to 7e to the j 2.1, that's exponential form of a complex number. We've got to find ln z in both the Cartesian and in polar form. Part D, we're given z is equal to 8 multiplied by e to the 1.5 minus j2. And again, if it helps you, you can think of the power being in terms of brackets. We've got to determine the ln z in polar form. And finally, part E, we've got to find in polar form, part 1, ln 2 plus j5, and part 2, ln of negative 4 minus j3. The answers are shown in the brackets on the right hand side. I would encourage you to start the presentation now and attempt exercise 9 before reviewing the solutions on the following slides. Exercise 9 solutions. Part A, we're given z is equal to 4 multiplied by e to the 1 minus j. We've got to determine ln z in polar form. So we take natural logarithms of both sides of the equation to get started, apply the first law of logarithms to the right hand side, and then simplify. The answer in Cartesian form is shown here, and then in polar form shown down here. Notice the phasor in this case, when we're working out our angle, lies in the fourth quadrant. In the final solution for ln z, the polar form is given in both degrees and radians. Negative angle because that's clockwise from the horizontal real axis. Exercise 9 solutions continue. Part B, we're asked to evaluate in polar form ln of 3 plus j4. So initially we convert from Cartesian to polar form. Now in this case the phasor resides in the first quadrant because we have a positive real value and a positive imaginary value in this particular case. Final solution shown down here for ln of 3 plus j4 in polar form, stated in radians here. Exercise 9, part C, we're given the complex number z is equal to 7 multiplied by e to the j 2.1, and we're asked to find ln z in Cartesian and in polar form. Again, you'll start by taking natural logs of both sides of the equation, applying the first law of logs to the right hand side of the equation, and then simplifying. That will give us the Cartesian form, and then we go into the r theta polar form. Note in this case the phasor resides in the first quadrant because we've got positive real and imaginary terms. Final answer for ln z given in polar form in both degrees and radians. Exercise 9 continue. Part D, we're given z is equal to 8 multiplied by e to the 1.5 minus j2. We're asked to find ln z in polar form. If it helps you, you can think of the exponents of the e in bracketed terms. Again, take natural logs of both sides, apply the first law of logs on the right hand side. Gives you Cartesian form, and then work out in terms of polar form. Note here the phasor lies in the fourth quadrant. We have a negative on the imaginary axis but a positive on the real axis. That's the fourth quadrant, so be careful of that. Answer given for lnz in polar form with a negative angle in degrees and equivalent negative angle in radians. Exercise 9 solutions continue. Part A, there are actually two subparts to this question. Got to find in polar form in part 1 ln of 2 plus j5. That's shown here. So the first thing to do is to calculate from Cartesian form to polar form. Note that the phasor in this case lies in the first quadrant because we've got positive, real and imaginary terms. So that gives the complex number in polar form, radians here. Then we're asked to find the ln of the 2 plus j5, so that's the ln of the polar form complex number here. We can write that in terms of the exponential form and then apply the first law of logs and start to simplify the solution. Notice the phasor lies in the first quadrant because both positive values here for the imaginary and real part. Final solution for ln 2 plus j5 is given here in terms of polar form and angle radians. Exercise 9 part E continued, and this is part 2. We're asked to find in polar form ln of -4 minus j3. So first of all, convert from Cartesian form into polar form. Notice here that the phasor resides in the third quadrant because we've got two negative values for our real and imaginary numbers. We work out the value of the complex number in polar form, then proceed to find ln of the complex number. This is the polar form of the complex number, and I've written it here in the exponential form. And then from there we can use the first law of logs to help simplify the problem. Answer given at the bottom for ln of -4 minus j3 in terms of polar form and angle in radians. Here's the bibliography used to generate this presentation. Again, as usual, I would strongly encourage you to refer to some of these textbooks, very good textbooks, for further reading on complex numbers. I hope this has been of interest to you, and thank you for viewing.